for number 22, they're asking us to figure out how old an ancient artifact is based on its C14, C12 molar ratio. And they tell us that this artifact has a 1/12 of that ratio as we would normally find today. Okay, so we know that when we're working with radioactive decay, we are always going to use first order kinetics. And the equations that I've written here are just kind of a combination of those equations. I've also gone ahead and converted the half-life into seconds, because generally with kinetics we're going to work in terms of seconds. So what that 1/12 is really telling us is that how much C14 we have now compared to how much it would have had initially is 1/12. And so that's going to be the inside of our log there. And they give us the half-life, and so we're just going to solve for the t in the numerator. So we'll have ln of 1/12 is equal to negative 0.693 times t that we're solving for, divided by t1/2, which is 1.8 times 10 to the 11th seconds. Okay, and so then it's really as simple as just doing a little bit of algebra and arithmetic to find that t is equal to about 6.45 times 10 to the 11th seconds. And hopefully you guys are all familiar with the conversions to take this from seconds to years. But we would have 6.45 times 10 to the 11th seconds. And we know that in 1 minute, there's 60 seconds. In 1 hour, there's 60 minutes. In 1 day, there's getting ahead of myself. Okay, there's 24 hours. And then in 1 year, there's 365 days. Okay, and so if you went through and did that conversion, you would get that this is about 20,466 years, which is essentially answer B. Okay. And you might be wondering, is this bottom part necessary? Could we have just done this problem in years? And in this instance, you could have actually just kept everything in years throughout. But I think it's good practice to work in seconds, because almost all of the kinetics problems we'll have to do will be in seconds. Okay, for number 23, we have another nuclear problem, except in this one, we're trying to figure out what the product of a fission event is. So we're starting with uranium-235, hitting it with a neutron, and out of that we get 3 neutrons, some krypton, and then some unknown. Okay. And so they tell us what isotope of uranium we have, but they don't tell us how many protons are in it, because we can just get that information from the periodic table. The atomic number for uranium is 92. And while we have our table out, we can go ahead and see that the atomic number for krypton is 36. Okay. because we'll need to know the atomic number to identify the product that we end up with. Okay, so looking on the left side of our reaction, we can see that we have a total of 236 particles to account for, and we have 92 protons specifically to account for. On the right, we have 3 neutrons and 94 particles from the krypton. We have 97 total mass particles accounted for already. And 36 of those are protons. Okay, and so we know we need to have the same number of particles on both sides of the reaction. And so we can just think 97 plus what would give me the 236 that I originally started with. And so from that we get that the mass number is going to be 139 for our X. And the number of protons that we'll have is 56. Okay, so hopefully you can see that now the right side is equal to the left side, where we have 92 and the 236. Okay, and then we just get our periodic table out to see which element is atomic number 56. And that is gallium. I'm sorry, that is barium. Mixed up my letters. Okay. So the answer here is A. Okay, for number 14, 24, Rickety Cat is trying to electroplate out some iron. Okay. And we have this equation that shows us taking iron ions, say that 5 times fast, out of solution to make iron solid. Okay. So he tells us the number of grams we need to make. Says that he has 8 hours to make these claws. We need to figure out what current we want to run the electrolysis at. And so it's important here to recognize that current is coulombs per second. And so that gives us a relationship to time. And our relationship to coulombs is Faraday's constant, which is on the data sheet, and tells us that Faraday's constant is 9.6485 coulombs per mole of electrons. Okay, so we as chemists never compare things in grams, right? We compare things in terms of moles. So I got the mass for iron from the periodic table and wrote it here. Now down below I can use that to convert to moles of iron. And I know that in Faraday's constant I have moles of electrons. So I want to convert to moles of electrons using that balanced reaction. So the stoichiometry of that tells me that for every 1 mole of iron that I make, I have to put in 2 moles of electrons. Okay, so you want to start with the balanced half reactions for these. Okay. And then I can use Faraday's constant to get us to coulombs of 9.6485 coulombs for every 1 mole of electrons. And then this ends up being 3.86 times 10 to the 5th coulombs. Okay, so now for figuring out the current, we have half of the problem. We have the coulombs, and now we just need to get the 8 hours into seconds. And so we start with what we're given, which is the 8 hours. And then we know that in 1 hour, there's 60 minutes. And that in 1 minute, there's 60 seconds. And so this is 28,800 seconds. So then our current is just going to be our coulombs per second. So we'll take our 3.86 times 10 to the 5th coulombs per 28800 seconds to find that we would need 13.4 amps. Okay, so that corresponds to to option E. Okay, for number 25, we want to figure out the hydronium concentration in the strontium hydroxide solution. So I think it's important to remember that strontium hydroxide is a strong base. So it will completely dissociate into strontium ions and hydroxide ions. Okay, so we know that 1.67 molar is 1.67 moles of strontium hydroxide in a liter. And that we're going to get 2 moles of hydroxide out of every 1 strontium hydroxide mole. Okay. So we'll have 2.34 times 10 to the minus 5 molar hydroxide. Okay. And so we can go ahead and use the relationship where Kw is equal to the concentration of OH minus, which we have, times the hydronium ion concentration, which is what we're trying to find. So 1 times 10 to the negative 14th is going to be equal to 2.34 times 10 to the negative 5th times X, or hydronium ion concentration. And we find that this is equal to about 2.99 times 10 to the negative 10 molar, which is C. Okay, so don't forget about your balanced equation. Okay, for number 26, I'm going to pick the solution that will have the most acidic aqueous environment. So let's go through and classify each option first. Copper chloride. Here we have a transition metal that's capable of accepting an electron pair. So this is going to be a Lewis acid, the copper ions. So that is capable of being acidic. Potassium fluoride. Potassium's negligible. Fluoride is the conjugate base of a weak acid. So this will be a weak base. Barium iodide. Both of those ions come from something that's strong. So these will both be negligible. Iron nitrate. Again, we have a transition metal capable of accepting a lone pair. So this is going to be a Lewis acid also. And pure water by definition is neutral. Okay, oops. So now we have to decide between copper 2+ or the iron 2+. So if you look at the periodic table, you can see that iron 2+ is actually going to be smaller than copper 2+, making it more what we'll call charge dense. So it will look like it's slightly more positive. Here you'll have like more positivity per square, or for the surface area of this iron ball. Okay, so this will be slightly better at attracting lone pairs. So this will be a better Lewis acid. Okay, so the answer here is D for iron.